Professor Emeritus at the University of Texas at Austin, and a distinguished visiting professor at the time at the Institute of Advanced Studies. Professor Uhlenbeck is one of the founders of field of geometric analysis, and her work had fundamental impact on many areas of mathematics and analysis, geometry, mathematical physics. And her impact is also reflected in the number of awards that she has received, and they're too numerous for me to list here, but I would like to mention among them her MacArthur Fellowship in 1983, National Medal of Science in 2000, Guggenheim Fellowship in 2001, Steele Prize in 2007, and of course the Abel Prize in 2019. She has been a role model for me and for many mathematicians, not only for her mathematics, but also in terms of her outreach activities, educational and professional development of young mathematicians, and especially women. So I really am so thankful to you. And today we're looking forward to her talk on Noether Theorems, then and now.
Thank you very much for the introduction. That's right. I first of all, thank you for the invitation. I have never been to Turkey, and I'm afraid at my age, I'm not going to make it. But I really like the fact I was turning down all invitations for many years because it's difficult for me to travel. And now with Zoom, I can actually accept some invitations. So I'm pleased at the opportunity to talk on Noether's theorem. 2 years ago, I had little interest in the topic. However, in the last 2 years, my research has led in a direction which altered my attitude. I read them in my present work, and I came to be sorry that I had not understood their role in several topics I tried to learn in the past. This talk is definitely from a mathematics perspective, but if I have time, I'll say a little bit about physics in the middle. So here's a rough outline of the talk. The first part is historical, and I'll explain exactly how they arose and what they did, and a few examples. And now I'll tell you, then I'll go on to tell you what their role is in geometric analysis. I hadn't realized their role in geometric analysis until I started talking on them, and then I found all sorts of places where they're actually appearing, although sometimes people don't realize they're the Noether theorems. So okay. Many people, including non-academics, became aware in 2015 that Einstein's theory of general relativity had been announced in 1915. This theory did not come out of thin air, and during its formative period, there were a group of mathematicians competing with Einstein as well as cheering him on. In particular, Einstein visited Göttingen in 1915 and gave a series of lectures which were enthusiastically received. A correspondence between David Hilbert and Einstein followed, and Hilbert himself made the contribution with a variational formulation of Einstein's equation. One of the puzzlements in the new theory that was no conservation laws from energy and momentum could be found for the new equations. These were readily discovered in special relativity, which had made clear the link between the two. In 1915, Noether had been invited by Hilbert and Klein to come to Göttingen and had probably been in the audience for Einstein's lectures. Miss Noether, as she was referred to at the time, was the daughter of a mathematician, Max Noether, and sister to another mathematician, Fritz Noether. At the time, higher education in women was not open to women. She had managed to write her doctoral thesis in 1907 in Erlangen under the supervision of the algebraist Paul Gordon. She had published a number of papers on invariant theory, and it appears that Hilbert simply assigned her the problem of looking into the problem of the lack of conservation laws for energy in general relativity. From surviving correspondence of the time, it appears there were preliminary results as early as 1916, but it was not until 1918 that the breakthrough insight which explained the problem came. Her paper, Invariant Variational Problems, was presented in July of 1918 with a dedication to Felix Klein on the 50th anniversary of his doctorate. That seems... Rather than start from scratch with definitions, I'll state the theorems and develop the ideas by example and clarification. What I say will be familiar to mathematicians and physicists alike. My apologies. If the integral I is invariant under a group G sub rho, then there are rho linearly independent combinations among the Lagrangian expressions which become divergences. And conversely, if the integral I, part 2 says, if the integral I is invariant under a group G rho sub infinity, this is her notation, G rho sub infinity, depending on rho arbitrary functions and their derivatives up through order K, then there are rho identities among the Lagrangian expressions and their derivatives up to order K, and conversely. So let's see a little bit what the integrals in Noether's theorem are of a very general form. And of course, she wrote them in Euclidean space, but you'll see as I develop the ideas that they naturally carry over to manifold, locally Euclidean space or a manifold. And here the function f, which y will be the function f, which is a vector valued, the symbols y sub k sub alpha indicate the partial derivative in the multi-index d alpha of the kth function is a multi-index derivative indicating the partials up to fixed order k, as this you'll find in every general PDE book. Of course, although we will now call f dx a volume valued function on the jet bundle. The function f is classically called the Lagrangian. However, Noether herself discusses symmetries of the Lagrangian density, which is the function times the volume integral. Dx here means dx to the m. So some of the first variational problems, like the Berkowitz-cone, like most of the ones we use in geometry, do involve minimization. However, many involve finding a critical point. At a minimum, or more generally a critical point, the first variation of the integral under an arbitrary deformation, which is classically called the delta u equals 0. It was a trick invented by Newton. The equations derived in this fashion are called the Euler-Lagrange equations. The general form of the Euler-Lagrange equations for most general examples of Noether's is a system of equations, and it's immensely complicated. I mean, I just write it out. This f sub y involves the partial of the function. F is a function of all the y's, and this is the partial of the function in the direction y, and this is the a multi-index partial derivative, and you sum over all the multi-indices and you get an equation. So Hilbert's integrand for general relativity, here the integral is the Ricci curvature and then the volume element, and you could write it out in coordinates, or you could write it out like we do nowadays, generally just invariantly. And the unknown now is, instead of f becomes g, which is a metric on a space-time. And the r of g is the scalar curvature, so it depends on two derivatives. And this volume element is the volume element induced by the metric on space. And the Euler-Lagrange equations are the Ricci curvature equals 0. And this is now thought of as a straightforward process of taking a derivative in a function space, but the old-fashioned language clarifies the geometry. So you have two approaches. You have the one that Noether took, where you write everything out in coordinates. And nowadays we've modernized, so we write very general things, but they actually mean exactly the same thing. And in some ways, the coordinate description is more enlightening. For general relativity, the partials up through order 2 are required, but for all but most examples in this, for all of the examples, it is sufficient to take L as a function of the derivative of vector value function of the derivatives of vector value functions and the functions. By invariant, she does not mean that the problem in hand is invariant. That is, if you have an integral that's defined on a bunch of functions, and you have a group acting on the functions, and the value of the integral is kept fixed, that is not what it's meant. What it means is the Lagrangian density itself is left fixed by the group action. And this is very confusing, and it remains confusing to a lot of people, but the notions are quite different. In fact, L only need be invariant up to a divergence or an exact n form. So you can actually major change your variables, and as long as L, as you get an exact n form out in the formulas, you can consider the integrand as invariant under that action. Hence, the theorem is local and not global in nature, and implies it was originally stated to local Euclidean spaces or manifolds, irrespective of topology or boundary conditions. The modifications needed when the image of F is in a manifold are easily encompassed in the theory, whether by using constraints and Lagrange multiplies or using local coordinates. And I won't be talking about manifolds. I'll be writing things out as in Euclidean space, although topology does enter later on. Let's see. Noether's theorem really uses infinitesimal symmetries, or the action of the Lie algebra. For practical purposes, however, a group action is far easier to identify. Her symmetries involve groups which act on both the domain and the range of F as needed in general relativity. Our examples all use either groups acting on the domains or groups acting on the range, and so we don't really deal with all the subtleties of her theorem. A rough idea is more proof, if her proof is more useful than the proof. To each of the row symmetries at the function U, where D, the variation vanishes, identify the infinitesimal variation of the function that comes from the symmetry. Noether gives an explicit formula for this in terms of variations in the domain and target. To apply the theorem in any given case, the first step is to compute them. So you need to know what these variations that come from the symmetry. Now you take these variations coming from the symmetry and you multiply them by an arbitrary function of small support. And compute the variation in this direction of this. Now the variations are a function space of functions with very small support. In general, for any integrand which depends only on first of derivatives, it looks like the variation of I has some formula which depends on the derivatives of the phis, and then it has a formula, a term that depends on the phis. However, the fact that this is an infinitesimal symmetry means this term actually vanishes. And so we now have a formula that said the variation, which is equal to this, zero is equal to this variation. And you integrate by parts, and the fundamental lemma of the calculus of variations tells you that for each B, the divergence VB is the sum, which is the sum of what you usually think of as in coordinates as derivatives equals 0. We'll get on to why this is not coordinate. From this, it's not hard to guess how to handle more derivatives, though it's much more complicated. And you have to integrate by parts a lot more anyway. In part 2, one knows that the variation vanishes up to a divergence for all F. So we don't need the fact we're at a variational formula to know that these divergences vanish. So they vanish. The divergence of this expression V vanishes for all functions f, not just the ones that satisfy the Euler-Lagrange equations. And Noether calls these conservations improper. And you'll see later on that they're actually not only improper, they're kind of silly usually. For physicists, they are true off-shell as well as for solutions. That was in case there are any physicists that want to understand. So some examples in n equal 1. So conservation of energy in one dimension is the easy example of part 1. And here we go from our domain variable x to the time t, because there's only one of them. In our simplification, every integral is of the form, the integral is the integral from two endpoints of f, which now depends on t, f of t, and f dot of t. F here is a multi-index, okay? The Euler-Lagrangians are just the equations as many as the dimension of the target. So this is d dt f differentiated in the direction of the derivative in the kth direction minus f differentiated in the derivative of kth direction equals 0. And so what if f is just a function of f and t, and there's no t in the formula for f, then f dt is invariant under time translation. In one variable, the divergence is ddt. An easy exercise is that the consequence of the Euler-Lagrange equations that if the function does not have a t in it, that E of u, which has a formula like this, you just plug it in and calculate it, is constant along every solution. And notice that to derive, I can't derive this. You don't need the function to be invariant. The functional might be an integral from A to B. The integral from A to B is not invariant under the time translation, but Noether's theorem applies because the integrand is. So in any case, this formula E is constant for every solution of Euler-Lagrange. This works for the n-body problem, geodesics on manifolds, and beyond. You do not need Noether's theorem to discover this, but it was Noether who pointed out this is an example of a general principle. A symmetry, such as time translation, leads to a conservation law, a number computed from a solution U, which is constant in time. While we are in n equal 1, we might look at an example of part 2 of the theorem. For a curve U in a manifold, we may choose to minimize length instead of energy. Then we have the integral is just the integral from A to B of the norm of the velocity computed. Now this norm can be computed as a function of t, but it isn't computed. There's no t in itself in this formula. Using the recipe above without restricting to U where the du vanishes, we come out with the mundane inequality that E, and then you write it all out what it is, and you get a formula, and you see that this is, of course, an identity, which is absolutely true. I'm sorry, I can't help it. The people are here doing the lawn mowing, and I have no control over them. I'm going to go close the windows. The second theorem explains that this mundane is because the translations are embedded in the group of diffeomorphisms at T, a group which depends on arbitrary functions on the line, and it leads to an identity that's true for all curves, not only those that solve the Euler-Lagrange equation. In this case, the identity is so trivial that it's hard to spot. This is similar to what happes, in fact, for the Yang-Mills functional, you'll find. Noether's theorem is quoted quite a bit in Hamiltonian mechanics. In fact, in many cases, this is what people identify Noether's theorem, which was what happens in Hamiltonian mechanics. This is not a theorem in Hamiltonian mechanics. Equating the two comes about from the classical Legendre transformation between the Lagrangian and Hamiltonian formulation of mechanics, and which is so it's a theorem in Lagrangian mechanics. It's not a theorem in Hamiltonian mechanics or symplectic mechanics. Or symplectic coordinate. Suppose now. So why is this theorem so modern? Because it looked like it was all in coordinates and, not very interesting to today's geometric analysts. But the domain variable in X in n dimensions, suppose the domain variable is X in n dimensions rather than 1. And we'll work our way down to 2 dimensions at the end. In part 1, Noether asserts that the finite dimensional symmetries lead to vector fields V with the divergence V is equal to 0. This looks impossibly coordinate dependent. Not so. After all, the formulas for the symmetries are coordinate dependent, but the symmetries themselves are not. If we incorporate the volume form dx into our thinking, for all functions with compact support at critical points, sorry, I left out the variation. Noether integrates this by parts, to get 0 equal to the integral of divergence of V times phi dx to the n is equal to 0, and applies what used to be called the fundamental theorem in the calculus of variations. That is if you, this is exactly the fact that if you integrate a function against an arbitrary vector function of an arbitrary function, then this divergence of V has to vanish. I mean, now what do we do to replace this? We write V inner product with the volume form. So this is a vector field. Then it has an inner product with the volume form, and this produces an n-1 form theta. And now our formula reads 0 is equal to theta wedge d phi. And now use the fact that this is the mathematical definition that the d phi, d theta is equal to 0 as a distribution. We don't integrate by parts because when we talk about distributions, we always talk about how they act on functions. The difficulties for integrands of higher order are significant and interesting, but our integrals are first order, so we don't have to get into them. I mean, that's when it becomes more complicated. But why is this known to Noether's contemporaries as a conservation law? Simply the divergence theorem. In our language, if S1 and S2 are two codimensional one submanifolds demanding a domain omega, then the integral of theta on the difference between the two boundaries is actually equal to the integral of d theta in the center, and which is equal to 0. And notice that to this day, one of the usual ways of applying this theorem is to take S sub t as constant time slices in an evolution problem and use the conserved quantity that the induced surface integral is constant on time slices. So which again is the way many people in special fields only know that as the conservation law. Okay, what about the reception? The Noether theorems are accomplished two things. They showed that many, if not all, of the known conservation laws in both physics and mathematics arose from symmetries. They also solved the problem assigned to her. Many energy conservation laws, such those of special relativity, come from translations in times, and those of momentum from translations in space. In general relativity, these translations are embedded in the group of diffeomorphisms, which leave the Einstein, Hilbert, Lagrangian invariant. Hence, they give rise to identities, not conservation laws. In 1921, Schouten and Stroop published a proof that Noether's identities for the Hilbert functional were equivalent to the Bianchi identities, which were actually known at the time. I'm sorry, I have another window to close. I should remember not to schedule any talks on Wednesday, because that's when I live in a condo, and that's when the Browns people are here. However, how were the theorems received? For much of this, I entirely rely on a reference by Kostman-Schwarzbach, which is called the Noether Theorems. Some attention was paid to them at first, with mention in correspondence among Einstein, Hilbert, Klein, and their associate. Her work was references in talks and papers in the next few years, but surprising little attention was paid to them in the ensuing years until the 1960s. In fact, they stopped kind of mentioning her when the subject came up. Kostman-Schwarzbach suggests two reasons. The importance of the variational formulation of problems in physics, and in particular the value of the variational formulation of Einstein's equation, was in doubt, and they did not seem to have applications. Well, I have to say that I am surprised, because in the 1960s, when I was a graduate student and I was reading things like Landau and Lipschitz and Gelfand and Fullman, I had the feeling that variational problems were really important in physics, but this is, I think everyone knows now, and you'll see in a moment why. So several revolutions and developments in physics and mathematics changed everything. First of all, the importance of group theory in quantum mechanics was discovered. Or I should say, in the process of discovering quantum mechanics, group theory turned out to be essential. And this established group theory and symmetry as a fundamental part of the mathematical language physicists use. The group theory was associated with classical field theory, which is often presented in a Lagrangian formulation. So, I certainly, when I learned classical field theory, it was entirely through Lagrangian formulation of field theory. So Feynman path integrals. Well, with the introduction of Feynman path integrals and the development of quantum field theory, Lagrangians and their critical points became suddenly central. Groups were already present. A little bit later, when gauge theory rose in describing fundamental particles, her discussion of groups modeled on arbitrary functions was a prophecy out of the past. Because she had simply written that into her theory as part of a general knowledge. I have to say something about gauge theory here, because in a way, at some point I got very interested in it, and I might or might not say something about it later. But the question is, why is Noether's theorem so important in gauge theory? And to tell you the truth, I still don't know, because when I asked the physicists, they gave me the answer that, well, if you had an integral that was invariant under a group, then the Euler-Lagrange equations were redundant. But an integral dependent on the group can be done in finite dimensions. That is, if you have a finite dimensional function and it's invariant under a group, then the critical points are invariant under the group. And that's not Noether's theorem. That's probably older than her theorem, and it applies in finite dimensions or not. So I still haven't solved the question of exactly why Noether's theorem was so important, but it certainly became, it's quoted all the time. The classical theory of completely integrable ordinary differential equations in Hamiltonian mechanics found its way into the development of infinite hierarchies of partial differential equations. And again, it seemed most of the applications in integrable systems seem to be through Hamiltonian mechanics rather than as true Lagrangian theorems in Lagrangian mechanics, field theory. And supersymmetry, and in some sense, I had spent a great deal of time trying to learn supersymmetry, and I think that I made a mistake in the sense that I should have started with the perception that physicists have of the importance of Noether's theorem and how the exact forms come out, and gone from there. And somehow or other, I just was left bewildered, mostly by what it's done. So I advise anybody who wants to learn about supersymmetry to go back and figure out what the physicists think about Noether's theorem. And when I did a literature search on MathSciNet when I was preparing this talk, and I discovered there's a tremendous amount of very interesting stuff in the applied mathematics world. It seems to be in the top layer of a toolbox, and the minute you look at anything, you look for a symmetry and you look for a conservation law. And there's a basic reference by Peter Olver. Okay, so why, let me see. Oh, yeah, there's one more page. The theorems were rediscovered many times, sometimes independently and sometimes from the papers themselves. In many of the new developments, there is only a faint shadow of the theorems themselves, but the association of symmetry and conservation is now an acceptable basic philosophy in physics and mathematics, which is an idea due entirely to Noether. And so you'll find references increase. So why am I interested in this? Okay, so in fact, unlike in applied mathematics and in physics, in geometric analysis, using Noether's theorem is not on the top layer. In fact, most of the applications of Noether's theorem actually are found without using Noether's theorem, because you can mess around and you can find them. And in fact, we came across exactly this problem. My former student, George Daskalopoulos, suggested we look into the analytic underpinnings of Bill Thurston's best Lipschitz map between hyperbolic surface. And I don't know. I'm assuming that people are familiar with Integrand theory, but let me just draw a picture that. So the idea is we have two Riemann surfaces, which are constant curvature, hyperbolic surfaces, and there's a moduli space of these. And we have maps from n to n, and we're trying to discuss the moduli space of different hyperbolic hyperbolic surfaces. And see how am I doing here? Now, the classical notions, there are several classical, the classical notion is due to Teichmüller. And you want to find a map between such surfaces that somehow has identified them. Teichmüller, a Teichmüller mapping is one in which there is one in which both surfaces are hatched, and the map expands along one set of the one foliation and contracts on the other foliation. I'm sorry, I assume everyone is familiar with Teichmüller theory. So there's the Teichmüller maps, which were used, the original ones, and nowadays people use harmonic maps as well. So, which is also, by the way, the integrand is just du integral m f is a map from m to n. It's just this map, and Bill Thurston made a suggestion that that we use, instead of the Teichmuller map or the harmonic map, the best Lipschitz map between hyperbolic surfaces. So if M and N are hermetic spaces, the Lipschitz constant of the map f from M to N is defined as the maximum distance of f of x, inner product f of y, over the distance of x and y. And all you need is a metric space to define these things. And in this case, the best Lipschitz map is a map from M to N such that the Lipschitz U, we want to find a best Lipschitz map, which is one such that the Lipschitz constant of U is less than or equal to the Lipschitz constant of F for all maps in the some class which contains U. And there's a 1995 preprint of Bill Thurston that proposes to base a Teichmuller theory on the properties of these best Lipschitz map between hyperbolic surfaces. While the preprint is still in circulation in familiar topologies, we're aware of no constructions tying this in with modern analysis. So this is a minimization problem. Is it connected with the calculus of variations? Yes, in the sense the problem can be approximated by integrals, and we are able to carry the conserved quantities from the integrals over into this limiting map. There is an extensive literature in the case of real valued functions in the form of infinity harmonic maps. In other words, the actual literature that we found on the subject is really just about taking a domain omega in, I'll do R2 because we're always in R2, and mapping it to the real line. So F sends omega to R, F restricted to the boundary, F restricted to the boundary is equal to F boundary fixed. So you fix the map. And so there's an extensive analytic map, theory about finding the best Lipschitz map in that class. It's called infinity harmonic maps. And so this is the only literature we could find about best Lipschitz constants is infinity. We were able to transfer this to the case of maps from M to F and from M to S1 or a real value line bundle. So we study this variational problem. We take this a variational problem, the integral of the derivative to the pth power integrated over M with respect to the metric. I mean, the metric on M is the key thing here. And the norm of the derivative is computed in the Riemann metric, and d mu is the volume form. In the place of boundary conditions, we minimize all maps in a fixed homotopy class. The unique up to rotation in the circle mu UP solves an equation like this. And we noticed immediately what turned out to be Noether's theorem. That is that we have the Euler-Lagrange equations look like this, but of course, the covariant derivative on forms is d is the same as d. The exterior derivative, covariant derivative is the same as the exterior d on forms. It's one of the first things you learn in Riemannian geometry. And so you get immediately that the derivative of this Lagrangian term is dv. And these are important, these are closed with important properties. And in our case, in the limit as p goes to infinity, the limits of v were least gradient functions of bounded variation. And in our case, we just did this problem and we immediately discovered we had something called transverse measures, which were essential in Thurston's work. In other words, in our very first attempt to doing this, to carry over our theory of of closed, in this case, n-1 forms, we were able to carry it over to the best Lipschitz came, and we came up magically with something that was important in topology. And I have to admit, we couldn't believe our luck. I mean, it was, we had no idea that we weren't looking for it. It just happened. But now we, of course, want to do the real problem, not the toy problem. We want to map m to n, where n is a hyperbolic manifold. And we found the right integrals, whose integrals approach the best Lipschitz maps. But we did not know how to find anything like this, this closed. We wanted to close some closed, we're on surfaces. n-1 forms are 1 forms, so we wanted closed 1 forms. And we wanted, so we knew that the transverse measure was important, but we didn't know how to find it. And so we then remembered Noether, and after messing around for a long time. So this is in the case F sends M to S1, the symmetries of the target are the rotations. And without following the recipe of Noether, we had found the closed 1 form corresponding to this symmetry. With this information, we now realized that we could use Noether's theorem. We now realized that we could use Noether's theorem. We were mapping M to N. And N is a hyperbolic manifold. It's a symmetric space, and it has locally an SO2-1 symmetry. Now, as you say, but it's not global. But Noether's theorem doesn't apply to global symmetries. It applies exactly to the case of local symmetries. So once we realize this, it's very easy to follow her recipe, which you can do with a little bit of calculus, in fact, and you immediately get some closed the closed forms that you're looking for. And so we managed to find a generalization of Noether's theorem to best Lipschitz maps. I should say they're not. Because there's a Lie algebra valued, they're Lie algebra valued, and because the symmetry is not global, it's only local. The conservation laws are sections of a bundle, but this is okay. Oh, and there's an interesting thing, which we have no idea. We found that some of the conserved quantities themselves satisfy dual variation problems of their own. And I don't have any idea whether that's been observed before or whether it's important or so forth. But this is the sense that well, in fact, I'm going to run out of time, so I'm okay. Now, on the other hand, what we didn't realize for a long time was that we were doing a theory in which we were mapping any surface to either a circle or a hyperbolic manifold. However, we just suddenly noticed that actually our surfaces, our domain surfaces, were in fact actually hyperbolic manifolds themselves. And so they also had local symmetries, which again is what Noether's theorem applies for Noether's theorem. And now the symmetries of the domain appear all the time in geometric analysis. The symmetries of the Euclidean group on a domain is the basic for classical concepts of laws of conservation and momentum. Standard textbooks show that for a function, which is for the Lagrangian, a function of only a vector value function and only its derivatives. Then, of course, the Euclidean group, doesn't matter what the boundary conditions are. The Euclidean group is a symmetry of this integrand. And classically associated with every solution of the Euler-Lagrange equations is a symmetric energy momentum tensor. I say energy momentum. Energy refers to when you have a time in your space that you're integrating over, and momentum refers to the spatial one. So we call these momentum tensors rather than energy momentum tensor. And it's a square tensor, and its divergence vanishes. Whether you take the divergence with respect to lows or columns, because it's symmetric. And somewhat is the same true if you had a Lagrangian. It turns out if you take a Lagrangian, which is a function of a map, and of course you have derivatives of a map from one manifold to the other, but if you actually have the domain manifold entering only through the volume element and a quadratic form, which means contracting in, you take the quadratic form, this is q squared, a quadratic form and contract it in these two, in the two domain indices, giving it a square term in the arrangement energy. So if you have an integrand that looks like that, you always get a momentum. So I mean, typical things would be harmonic maps. And actually, if you really want to extend it a little bit, you can do Yang-Milson's way and so forth. In this case, there is a momentum tensor, which is a section of the symmetric tensor of symmetric product of forms, one forms, which is associated to any solution of the Euler-Lagrange equation, which now defines the fact that the covariant derivative of the dual, or I should say the divergence in the covariant derivative of S with respect to either rows or columns, again, is equal to 0. And these equations abound in geometry. I mean, I'm not sure the equations abound, and I'm never even really sure exactly how many there are, but I showed it to my friend Julianne Turn, and she told me immediately about someplace in minimal surfaces where they come up, which I didn't know about. So consider that, okay, sorry. Okay, so now what do they have to do with Noether's theorem? Well, suppose we have now a local isometry group on the domain, okay? And we have this equation, d star s is equal to 0. Well, the theorem, which is very easy to prove, is that in that case, the regular covariant derivative, the dual of the covariant derivative, the regular divergence, of the n-1 form here of S contracted with the local killing field is always 0. So so you get immediately out of the fact that you have an equation like this on a manifold with a symmetry. You immediately get out of this. The divergence of a one form vanishes, so it's the exterior derivative of an n-1 form vanishes. And this is packaged in a global theorem identifying S. Well, we have, okay. And I should say that there's an ingredient lacking. The tensor S is symmetric in its indices, which was classically important, but this symmetry is not reflected in this proposition. And so anyway, I'm getting close, even with the extra time, to my 50 minutes. I think I'm going to go on to examples, because I was going to talk a little bit about the symmetries of the domain. Well, I'll just state the theorem. If you have a locally symmetric surface and you have this equation, which I said d star s is equal to 0, then this is valid if and only if the function E in the covering space M such that the dual one form in both indices. This is a one form. This is a symmetric symmetric product of one forms on the right hand side. This S is actually equal to the covariant derivative of the derivative of E plus the scalar curvature times the metric tensor on the surface times E. And this is this formula here. And I should point out that people know the S is very often a quadratic differential, but I've never seen anybody write that formula down for what the quadratic differential looks like. So in this case, so anyway, again, this is a problem. This is a question. I have no idea whether this is an important observation or not, but it's yeah, okay. Okay, well, I want to say a little bit. I won't say too much about the examples, but I want to. Actually, the first one is I've given this talk before, but the first one is one that I just added because I was idly looking through the conferences, and lo and behold, I found a conference on constant mean curvature surface and conservation laws. Well, these conservation laws for constant mean curvatures in a symmetric space, which is S3, H3, or R3, all have the symmetries of the domain of the target S3, H3, or R3 are reflected in conservation laws for integrals like the integrals used in constant mean curvature problems. And in fact, I had been aware of this for a long time, but I hadn't realized that there was actually a lot of active research going on this right now. So I'm willing to bet that very few people realize that this is just a simple application of Noether's theorem. Another place where they've appeared is in the Wilmore functional, where in the Wilmore functional, the F is a map from M into R3, okay? And this curly H of F is the second fundamental form, and of an immersion, and we integrate this and we get the Wilmore functional, which is an integral of M, and then you use, of course, the induced metric on the surface to take the integral. And the problem is to find a minimum when M is a torus, or it's actually not that's not really the problem. It was known that it was suspected that the Clifford torus was actually a place where the minimum was taken on, where T2 is S1 cross S1, which naturally sits in R2 cross R2, but S3 sits in R2, and this in fact sits in the R3 here. So, and S3 is R3 union infinity. And the reparameterizations form its symmetry dependent on two functions of two variables, and the Euclidean group acts on the targets. The special property of this integral is that it is also invariant under dilations in R3, implying that it is invariant under the full conformal group of R3 union infinity, or S3. The calculations needed to carry out Noether's theorem in this case are more difficult than any described in this talk. The conservation laws obtained from these symmetries have been discovered without appealing to Noether by Riviere and used in his solution of the Wilmore problem using partial differential equations. And at the end, I'll show you a reference by Bernard, who derives these identities from Noether's theorem directly. And so that's, but this is a typical case where the conservation laws can be discovered without Noether. I just suspect it takes a lot more work. Sorry. Okay, well, yeah, maybe I'm really at the end of my time. I mean, I know it's I have 50 minutes, which is what I was given, and so. But on the other hand, I think I'll.
Well, you can maybe give one more. It's okay because we started late as well. So.
Yeah. Oh, well, sure. This one takes a few minutes. I mean, the symmetries of the domain. And without, of course, many people have actually used and have used things like the monotonicity theorems. And the monotonicity theorems, in the monotonicity theorems in flat space for geometric integrands are a consequence of d star s is equal to 0 for the momentum tensor. That is, that's known in classical physics, that if you have an integral in Euclidean space of that form, you're going to get an energy momentum tensor, and it's going to have d star of s is going to be 0. And on manifolds, of course, you don't have d star s is equal to 0. You have the covariant derivative of equal to 0, but it gives an approximate monotonicity, which is plain good for estimates. So all these monotonicity theorems are actually simply applications of Noether's theorem for the symmetries in the domain. Okay, I wanted to mention one example, because this is, so my colleague Antonella Grassi heard an earlier version of this talk and pointed out to me a very recent paper in physics using Noether's theorem. I hesitate to include it because the physics constructions need a lot of translation to be understandable to a mathematician. The paper is A Shorter Path to Celestial Currents by Sabrina Pasterski. It derives the word identities of Strominger to identities based on the conformal compactification of space-time. And I had actually been aware of this work, and it did look like something that we could look at. But basically, it's based on. Oh yeah, the calculation based in the paper rely on a moment map formulation of gauge transformation. And in such, it falls into the mathematical realm of Noether's theorem in Hamiltonian mechanics. Sorry, I seem to have gotten this mixed up. Okay, anyway. Oh, well, let me just say that there's the moment map formulation, moment map formulation of gauge theory. It applies only to surfaces. So to surfaces, and actually, just as a reference, many mathematicians are familiar with it because it's described in the famous paper of Atiyah and Bott on Yang mills on a Riemann surface. And so this moment map formulation is apparently well known to physicists, and actually in the problem that she considers, it's to do with the conformal compactification of space-time and how conservation laws can be matched going forward on the forward cone with the backward cone. And as I said, it does rely on surface integrals in the problem. Anyway, yeah, I think that's about. Let's see. Right. So I thank you for your attention, and sorry about the lawnmower.
Thank you very much.
Yeah.
Nice.
Yeah, I was going to say this paper is a good one for background. And anyway, thank you.
Thank you. Thank you. Are there any questions? You can unmute yourself and ask if you want.
I have one.
Mm-hmm.
Okay,
Please.
thank you very much for a great talk. Actually, I want to ask about this reference you just mentioned, Jan Bernard's. So
Yeah.
this conjecture, I mean, Marquez and Neves told like 5-6 years ago. And does Bernard gives an alternative solution to that, or just make this conservation laws connection with the Noether's theorems?
Sorry, I didn't.
Okay. Artes and Neves solved this Wheeler conjecture like 5-6 years ago.
Yeah. Uh-huh.
Yeah. So in this paper, so Bernard gives an alternative proof for this, or just makes a connection with the conservation laws and Noether theorems for this Willis function.
Yeah. Sorry.
Yeah. Does Bernard give an alternative solution to Willis conjecture in this paper?
Oh, really? Uh-huh. I didn't know that.
No, I am not. I am asking. I don't know.
Oh, no, no, no. Sorry. So Wilmer's conjecture had already been solved. What
Yeah.
Bernard did was show that the identities were discovered by Riviere, right? And but it turns out that they follow from the identities follow from an application of Noether's theorem using the conformal symmetries of the target manifold. So it's an after the fact observation. You see, and as I said, I think I pointed out in several, in fact, all the examples, frankly, in all the examples I know where Noether's theorem is actually used in geometric analysis, the identities were discovered without using Noether's theorem. That is, they were discovered from scratch. You know, you can mess around a long time, and in fact, however, we could not do that with our problem. We had to actually use Noether's theorem from scratch, writing down exactly what she said to do, you know, and which, I mean, I didn't follow any modern description. I went back, you look at Noether and you do exactly what she says to do, and lo and behold, you get a conservation law, right? It's, it probably needs to be better known.
Yeah, thank you very much.
Thank you. Are there other questions? Okay. If that's not the case, we thank Professor Uhlenbeck once more. And
Yes, unmute ourselves and just give a applause. Yeah.
yeah.
Thank you.
Thank you.
Thank you very much.
Thank you.
Thank you.
And this